Record to the computer. Hello, everyone. This is Team Pebbles, and we're excited to share our work with all of you. So who are we? I am Balnur Mindagalieva, and my teammate is Dinara Sagalieva. I'm a PhD student at Colorado School of Mines, whereas Dinara is a machine learning engineer at Charité. I'm located in Lakewood, Colorado, and Dinara is in Batumi, Georgia. A cool fact about us is that we met in 2013 in England and have been BFFs ever since. Moving on to problem statement. As we all know, we were provided the model results with the goal of obtaining a theoretical optimal placement of the production well to ensure that the net energy and electrical power output would be maximized over a 20-year period by honoring the parasitic losses. So the task itself is quite challenging. So our objective was to focus on building machine learning models capable of predicting the single flash Rankine cycle net electrical power output with 100% generator efficiency and the net output power with parasitic losses. And then these models can further be used for optimization purposes. Our workflow was the following. A good amount of time was spent on understanding the data. Then we applied data engineering, like creating the necessary target columns. Then we used feature engineering in order to select important features. And lastly, we built a number of machine learning models. Our work is mainly focused on the data coming from the medium 20-year CSV file. Moving on to prep processing. So a number of steps were taken in order to sort of transform the time series data into a usable format for us to create the machine learning models. So we used the objective function provided to us, and then we determined the cumulative net power, P usable and P out, with the 100% efficiency. So here, enthalpy at 95 degrees corresponds to the output result from the model. T stands for the time step, and N corresponds to the cumulative of 20 years. Then we applied the expected or ideal relationship, let's say, between the following three variables in order to filter the data for further usage. Afterwards, we applied a predictive power score analysis, which is a powerful analysis and usually preferred to the correlation matrix. We did that for both target columns, P usable net and P out net, and that helped us to have an insight into the linearity between the features. And in this case, we picked the independent columns as illustrated down here, which are the same for the both cases. Next, we applied what's called a greedy feature selection while keeping in mind the information learned from the PPS analysis. Again, it was done for P usable net and P out net. And that helped us to determine the main three features or columns that have the highest contribution, importance, or the lowest linearity, as we can see outlined for the both cases. Moving on to models. So firstly, we applied a regression. The goal was to predict the P usable net and P out net values, given the following input values that were shown in the previous slide. And then we applied a standard data normalization procedure by using min-max scalar for features and logarithm for target columns. And then we split it into a train and test with the test size of 0.3. Then we used three models, AdaBoost, Random Forest, and XGBoost, with hyperparameter tuning to compare different model performances. So here we see the results for P usable net and P out net. As we can see, the right results illustrated in the right are performing better. The best model is the Random Forest. Even though the test score is quite low, still on the right-hand side, we can see it's not as overfitting as on the left-hand side. After finding the p-usable net and p-out net, we wanted to find or see the number of rows that hit the target. And by the target, we mean that we applied just a simple percent error formula using the relationship between capital Q and small q in here. And that gave us an idea to use classification to predict the placement, whether the placement of the production well was actually successful for the ideal case. And we take advantage of binary classification using decision tree classifier and logistic regression with hyperparameter tuning and cross-folds. Since there is a multitude of rows that don't hit the target, it was essential to check whether class imbalance is present. Of course, as in real case, there was such an issue with class imbalance where the true values, so the values that hit the target, corresponded to 20%. So the next step was to deal with this imbalance by applying a number of treatments. So mainly we use two, which is undersampling and oversampling. Each treatment scenario has its own advantages and disadvantages. While the first increased the true positive values and drastically decreased the true negatives, the second treatment actually did quite the opposite. And since the accuracy is not the best scoring method in classification problems, we use confusion matrices and RUC AUC scores to measure the performance of the models. Here we see a classification undersampling. In the case of the logistic regression, it performed a little bit better than the decision tree classifier, with a 1% increase in the train and 3% increase in the test scores. So here we see the results. As for oversampling, both actually had a very close scores. However, the difference lies in the true negative and true positive ratios. In summary, we applied a regression. So random forest regressor model had the best performance out of the three implemented models, AutoBoost, RF, and XGBoost. As we can see, the results for random forest are outlined here for p-usable net targets and p-out net targets. For classification undersampling, logistic regression did slightly better than the decision tree classifier, and here are the scores for logistic regression, whereas oversampling, both logistic regression and decision tree had nearly identical performance as shown down here, which is actually very close to the values we got in the second case. So moving on to discussion. We also looked at the simultaneous occurrence of the following two ideal relationships, where again we use the relationship between small q injection and capital Q injection, as well as the assuming that the number of fractures intersecting the producer equals the number of fractures intersecting the injector. Then we sorted the data in a descending order of p-usable net and p-out net. So here are those two columns, the first 10 rows from the median 20-year CSV file. However, the VTK files were not provided for that data set. So we looked also at the more wells 30-year CSV file. We can see that p-usable net values are quite large. That was an interesting occurrence that might be investigated further by implementation more complex thermodynamic functions. However, we decided to go ahead and look at the very top values for the p-out net and p-usable net, which we will see in the next slides. So meaning that we made an attempt in visualizing the 3D geometry data. And here we have a table illustrating the parameters of the placement of this well for instance, we see that the spacing is 703 meters, whereas the length is over 1100, and that was for P out net as a target column. And same for the P usable net. So here we see a larger number of wells since it's coming from the more wells file with the spacing of 480 meters and the same length as in the previous case. So in conclusion, we built multiple ML models illustrating a reasonable performance of predicting P usable net and P out net. Given the challenge and uncertainty behind transforming the time series data into a suitable format for our analysis, the introduced models do lay the foundation for the optimization of the production well placement, which by itself is a puzzling task. And of course, stronger technical knowledge and nuances of enhanced geothermal systems is necessary for tackling the problem of the Datathon. Thank you.